Okay, so we are starting part 2 of lecture 4. Let me share the screen with you. So can you see my screen clearly? Do you see my screen? Okay. Thanks. Okay. Let me continue a little bit on the subject, and then we stop for the discussion of the exercise. Speaking about exercises, yesterday I sent you an email with the first assignment. Okay, so you can find the assignment in the website of the course. I hope you all managed to access it. So can you confirm that you managed to get it? Okay. Okay, thanks. Okay, so let me just quickly recap what we were discussing before the break. We were discussing that Fraunhofer was passing sunlight through a prism, and what he detected was that the spectral decomposition of the sunlight was such that he saw these dark lines, which are also called Fraunhofer lines, in the spectrum. Namely, some colors were missing. Okay, so you can now reproduce Fraunhofer's experiment, but instead of taking sunlight, you can, turn on a flashlight and direct the light to. Okay, so I will answer the questions regarding the assignment later on. Oh, okay, John. So just a second. Okay, so if you turn on a flashlight and you send light towards an ampoule made of glass with some gas, okay? So the setup is the following. You have a flashlight, you send light to an ampoule that contains some gas of some atomic species, okay? And then after light passes through the ampoule, you can just pass the outgoing light to through a prism, and again see the spectral decomposition of the light. And if you do that, there is a question in the chat. If some colors are missing, does that mean some of the rays of sunlight? Yes, this is exactly what happens. And now, if you perform the same experiment with this gas inside, some tube of glass, and pass the outgoing light ray through a prism, what you're going to see is that the profile is exactly similar to what Fraunhofer saw. But it doesn't mean that you're going to see the same dark spots in the same values of wavelengths. But what I mean by that is that you're going to see a spectrum of colors with also some dark lines. And this means that when you pass light through this gas, the atomic species that, compose the gas will absorb also some colors from the light ray that you send. So again, what is going on? You send light through a glass tube, and the atoms that compose the gas of the inside this glass tube will absorb some colors, and others will just pass through, and you're going to see them in your spectral decomposition. And what is fantastic about that is the following. Let's say that you do this experiment for some gas of type 1. You have some random gas that you know what is it, and you detect what are the colors that are missing. And you see that you are going to see some profile of dark lines, okay? Now you go to your lab, you just change the gas inside this tube, you put a different gas with a different with different atomic species, and you throw light again, and what you're going to see is that the colors that will be missing in the spectral decomposition are different. So for different materials, different colors will be missing, okay? Now, assume that you can do that for several different materials. So you change the gas, and now you change the gas again and again and again, and you see that every time you change the gas, a different collection of colors will be missing. Okay, and now let's assume that you just write down all the colors that are missing for each material. Then I can reverse the question, okay? I can think as follows. Assume that you don't know what is the material that you put. Okay, I will repeat. So let me repeat. I'm saying that when you pass light through this gas inside a tube, a glass tube, some colors will be missing in the spectral decomposition, okay? If you change the gas, you see that other colors will be missing. So the colors that are missing will depend on the gas, on the type of the gas that you are inserting in the glass tube. Okay? So if you change the gas, you change the colors that are missing. So there is a correspondence between the atomic species that made the gas and the colors that are missing in the spectral decomposition. Okay? So you can either know what is the material and then say what will be the colors that are missing, or you can check what are the colors that are missing and say what is the material that was inside the tube. So the colors that are missing in the spectral representation of a radiation is like a fingerprint of the material. So each material will tell you, each material will absorb a different collection of colors. And this is a very important remark, because this is exactly what people used, for instance, to tell what was a given star made of. So if some star emits light, you can take the light that was emitted by the star, you can pass the light through a prism, and then you just see what are the colors missing. And because we know already a lot about how different materials absorb light or different colors, you can tell, well, in that star, I know that there is this and that components. So the spectral representation or the absorption spectrum of a given material is a fingerprint that will tell you what is the material that is absorbing the colors of a given radiation. Okay, this is very important. But now I can ask a different question. Okay, so this was about radiation that was absorbed by a material. But we also have learned that materials or atoms can emit radiation. And now I can do the following. So if I have a material and this material now emits light, I can pass through this light emitted by the material and ask what is the spectral representation or the spectral decomposition of that. Okay? And how can you make a material to emit light? Well, you just hit the material, right? Think about a lamp. When you pass through an electric current through the lamp starts emitting light, okay? Now you can take the light emitted by the lamp, pass through a prism. So this was uh, light emitted by a material, and you can pass through a prism and tell what is the material that makes the lamp, okay? So this is in contrast to what we discussed before, which was the absorption spectrum. This is what is called the emission spectrum, because you're really measuring the emitted radiation. Okay. So, but now you can ask, okay, so what? I mean, I have I know how to measure the absorption spectrum of some given radiation that passed through some material. And now you are telling me that I can measure the spectral decomposition of emitted radiation by some material. Okay. Now let's, is there a natural spectrum in the, so the atmosphere is made by several different chemical components. So you have to, I mean, that depends a lot on these components. But you can use this technique to discover what are the elements that compose the atmosphere. Okay.
Hello.
Hi.
Please, it's still not clear for me how we can detect or see the missing colors. Are we comparing it, the result with the main one who Newton made it? Are we compare this to output and see which color is missing?
So what is going to happen is that you see, when you are measuring the absorption spectrum, you see an entire range of colors going from the very high frequencies to very low frequencies that your eye can detect. And in between, you're going to see dark lines, okay? So you can really tell what is the missing frequencies in your spectrum.
Does this mean we will see the missing colors directly after the prism?
Yes, so you're going to see dark lines, and this is exactly the missing colors.
Okay.
Okay?
Okay, thank you.
Okay, so what makes us see the sun rays as white light? No, I mean, so you see that the light that comes from the sun comes as white light, and the fact that there are missing colors, it's not visible. You can make that visible by passing the sunlight through a prism. What happens is that different colors will travel through the glass of the prism with different speeds. So this is the phenomenon of refraction. And you see that some lights will curve more and some lights will curve less with respect to the incident angle. And this is precisely what makes you able to detect different colors. Okay? So if you do not pass sunlight through a prism, you are not going to detect the missing colors just by a naked eye. Okay? Okay, so coming back to the emission spectrum, well, now you are trying to detect what are the colors that a given material can emit. So let's take, for simplicity, the simplest atom we know about, which is the hydrogen atom. So the hydrogen atom is the simplest atom, and if you want to explain the emission and absorption spectrum of some atom, we better start with the simplest one. If you can't explain that, then we don't need to move to more complicated ones because we simply don't know. It turns out that I put this figure here, which is the hydrogen spectrum. So below, you're going to see the absorption spectrum, which is the spectrum that you see, for instance, if you construct a tube of glass filled by hydrogens, so you have a gas of hydrogen, and if you pass light through this glass tube, you are going to see, after passing the outgoing light through a prism, you are going to see that these wavelengths or these frequencies will be missing. Okay? So you're going to see these dark lines in the spectrum of the absorption spectrum of hydrogen. Okay? Now you can reverse the question and you take a gas made of hydrogen and you heat up the gas. And as you know, this gas will now emit light. And you can pass the emitted light through a prism. And what you see is that the emitted light by the hydrogen gas is precisely the complementary picture from the absorption spectrum. So the emission spectrum will be all dark except from these very, very particular lines, you see, that are missing in the absorption spectrum. So, in other words, the hydrogen will absorb these specific colors that are dark in this representation here, but the hydrogen will just emit exactly those lights that it could absorb. So the emission spectrum is again a fingerprint of a material, of an atomic species. I can tell you what will be the colors emitted by hydrogen because all the time you heat up hydrogen, it will emit exactly these colors. So if I do that once, I can take a note of the colors that hydrogen emitted. And if someone else, several years later decided to heat up hydrogen, this person will see exactly the same emission spectrum that you saw before. So I can tell you what is the material that you are heating up just by looking at the spectral decomposition of the light emitted by this material or the absorption spectrum, namely, if I pass light through this material, I will know what will be the colors that this material will absorb for it. Okay? Now comes a very interesting question, which is the following. From the classical theory, I can exchange energy with the material continuously. So I can give any amount of energy I want to the material. And in principle, if I excite this material to some high energy, this material can emit whatever quantity of energy it can. So, from the classical theory point of view, there is no reason for having these discrete sets of colors that are absorbed or emitted by a given material. Okay. So how do we explain that? What is what? How do you explain that a given material just absorb specific colors of radiation and just emit specific colors of radiation? This is not something that is described by the classical theory. Okay. Okay. So the explanation for that will come tomorrow with the model described by Niels Bohr. But before closing the session and discussing the exercises, I want to tell you that a Swiss high school teacher called Johann Baumer, he was looking at, this picture here, which gives you a discrete set of dark lines. And he was thinking, well, is it possible to describe where these dark lines sit in the wavelength spectrum by a mathematical expression? So he just asked this question, and just by looking at this absorption spectrum that he knew the values, Baumer wrote this formula here. So he's saying the following. 1 over the wavelength, so the inverse of the wavelength, will be a constant, which is called the Rydberg constant, times 1 over 4 minus 1 over n squared. And n is a natural number that counts exactly the fact that you're dealing with a discrete set of dark lines. So if you plug n equals to, and another comment is that n starts from 3. So if you plug n equals to 3, 4, 5, and so on, you're going to detect these values of wavelengths that are missing in the absorption spectrum. And this equation that was totally empirical, I mean, there was no fundamental explanation of why this equation was true. Baumer just noticed that he could describe these lines by this equation, but doesn't mean that he had an explanation for why this worked. And for that, he has also to introduce this constant, which has this value, okay? And what is fantastic is the following. So Baumer could see, the spectral decomposition and therefore the dark lines in the visible region. So just a second. So Baumer could see, could predict what were the values of the missing colors. But then he said, well, if this equation works for these values that I see in the visible spectrum, maybe this can also work for whatever value of n I choose. Okay? So if I increase the value of n, so I'm seeing here a couple of lines, but if I keep increasing the value of n, this would predict another line and another line and another line, and we just don't see it because it's not in the visible region. Okay? And what is fantastic is that he was correct. So this formula is not restricted to these lines. But of course, you can make more generalizations. For instance, you see that here you have 1 over n squared, and here you have 1 over 4. Well, 4 is 2 squared. So I have here a number squared. I have here a number squared. If I replace 2 squared by m squared, right, I will have 1 over m minus 1 over n squared. So I have m and n. And you have this more general formula here. And with that, if you choose a given m, you can just extend n to m plus 1, m plus 2, and so on. And you are going to keep predicting more and more missing colors in the spectral decomposition. And what is fantastic is that this is verified experimentally. So just to make clear, this is not magic. I mean, he didn't have an explanation for that. But he was seeing some experimental data and was making a guess, an educated guess, for a mathematical equation that could explain that. He found such an equation. And then he said, well, now that I have an equation, I can try to extrapolate the limits of what I know for what the mathematics tells me. And it worked out. Okay? So what happens experimentally if, I think you mean infinity, if m goes to infinity? Yeah, so if m goes to infinity, you see that m, it's a problem, because if m goes to infinity, there is no n that will be greater than m, because you see that n has to be greater than m. But of course, you can take n to infinity, and there's nothing wrong. This term here will just vanish, and you're going to have a prediction for the wavelength when you choose a value of m. We are going to see that actually tomorrow. When n equals to 3, which wavelength it will give us? That's a very good question, Mahmoud, and I invite you to do the calculation yourself. So here you have all the information, right? So you have here, you just replace n by 3, you're going to have 1 over 4 minus 1 over 9, and you can just work out this calculation and figure out what is the value of lambda. This is a very simple calculation. And I invite you to tell me where in this spectrum this wavelength will sit. Okay? If you have some troubles with that, just let me know. We can discuss that tomorrow. But now, in the remaining 20 minutes, I want to go to the exercises about the photoelectric effect and ask you about and discuss with you. But before that, there was a question about the assignment. Let me check again. In regard to the assignment, when finding the kinetic energy, do you use the standard electron mass, or it will always be defined? So when I ask you about the kinetic energy, the kinetic energy is, if you want to think at low velocity regime, this will be 1 over 2 mass of the electron velocity squared. And the mass of the electron you can find in Google. I mean, you can just type the mass of the electron and you're going to get the number. This is a universal number. Okay. Okay, so exercise number 1. Can you tell me who tried to do it and who didn't? I mean, just tell me who tried. Okay. Okay, good. Good. Okay. So those that tried, what was the value of, I mean, what was the result that you found in number A, in letter A? So someone said 300 meters. And the rest? 3 times 10 to the squared, which is 300. Yeah. Okay. So I see that all of you that answered found 300 meters, and this is correct. Okay. So, okay, let me, yeah, so I want to, maybe I can try to do it here in a small. So consider a radio station that emits radio waves at frequency of 1 megahertz, which is 1 times 10 to the 6 hertz, and at power 5 kilowatts. Item A, compute the wavelength of the emitted waves. So item A wanted to ask you what is the wavelength of the emitted waves. Well, we know that there is a relation between wavelength, frequency, and the speed of the wave, right? So we have learned that the speed of the wave is equal to the wavelength times the frequency, right? But this is a radio wave, so it propagates with the speed of light. So V is nothing but C. Okay? And the frequency, and C, we know what is the value of C. C is 3 times 10 to the 8 meters per second. Okay? And also, we want to discover lambda, which is the wavelength. We have V. V is equal to C, which is equal to 3 times 10 to the 8 meters per second. And nu is the frequency, and the frequency is given by the problem is 1 times 10 to the 6 hertz. So I know C and I know nu, so I can find what lambda is. Lambda is just C over nu, which is 3 times 10 to the 8 divided by 1 times 10 to the 6. Well, this will give 3 times 10 to the 2. And what is the unit? The unit is meter. Okay? So this is 300 meters. Okay? Is that clear to everybody, or some of you did not understand? Please just tell me. Okay, it's clear. Okay. Now, item B is compute the energy transported by a single photon. Okay, so a single photon transports energy that is E is equal to Planck's constant times the frequency, right? So H is a constant that has a fixed value. So we just look at your notes and you're going to find the value of H. And nu is the frequency of the radiation. So you just replace H by the value of Planck's constant. And here you have to be careful because you can use H in units of joules times second, or you can use in electron volts times second. So if you use in joules, this will be 662 minus 10 to the minus 34 times the frequency, which will be 1 times 10 to the 6. And well, this is a simple calculation. You just multiply the powers of 10, and this will give to you 6 minus 6.62 times 10 to the minus 28. And since I used the value of Planck's constant in joules times second, this will give the result in joules. But I could have asked you to compute that in electron volts. Then you just had to use the value of H in electron volts and multiply by the frequency, okay? So you can do that if you want. And item C is how many photons are emitted per second? Well, you have the power of the source. The power is the energy divided by units of time. So you're saying that at 1 second, you emit 5 kilojoules. So the power is P is the energy divided by time interval. So the power will be 5. This K corresponds to 10 to the third. So this will be 10 to the third. And this is energy divided by delta T. Okay? But the energy is nothing but the amount, the quantity of photons times h nu, right? So you just write the energy as being the number of photons times h nu, and this is divided by delta T. So you want to have the number of photons divided by time, the number of photons per second. So you just have to bring h nu, sorry for that, you just have to bring h nu to the left-hand side of this equation, okay? So this will be equivalent to, let me write like that, this would be n divided by delta T will be 5 times 10 to the third divided by h nu. And h nu you already computed, okay? So the result of this, so it's becoming really short here, so I'll write the answer here. The result will be around approximately 7.5 times 10 to the 30 photons per second. Okay? That's the answer. Are there questions about that? Okay, so why did you multiply by n? Yeah, so the total energy transported by the radio wave will be the number of photons that, you know, are part of the beam times the energy of each photon. So if you have a collection of photons and you want to know what is the total energy, then you have to know how many photons you had there and multiply this number by h nu. This will be the amount of energy that, you know, flowed to the per second, per unit time that you make this measurement. So delta t is still here. I'm dividing n by delta t. This is the number of photons per unit of time. This is what I want to compute. So I just keep this here. This is something that I don't know. I want to discover what is the value of n divided by delta t. So 5 times 10 to the third is the power. So the power is given by the problem. The problem says that the power is 5 kilowatts. 5 kilo means 10 to the third. So the power is 5 times 10 to the third watts. Okay? Okay. If there are no further questions, I will move to problem 2. Problem 2 says, well, the threshold wavelength for the occurrence of the photoelectric effect in aluminum is 2,1954 angstrom. This is equivalent to this expression here. And I want you to compute in item A the work function of aluminum. Okay? So what is the information that we have? We have, first of all, that the value of the threshold wavelength. This means that below this value of the wavelength, sorry, above this value of the wavelength, I don't have the photoelectric effect. Okay? So this means, if you remember the equation of the photoelectric effect, the equation is the kinetic energy of the electron, the maximal velocity of the electron, is equal to EVB, which in turn is equal to h nu minus the work function. Okay? I'm saying that I can also relate the frequency with the wavelength. So this can be written as h c over lambda minus the work function. Okay? What I'm saying is the following. The threshold wavelength is this number. This means that this is the value that when I replace lambda by it, this gives hc over lambda minus w equals to 0, because this is the threshold wavelength. So this is the value of the wavelength for the photoelectric effect just occur. If I give you a wavelength that is greater than this wavelength that I said, this number will be smaller, and therefore the work function will win over this energy, and the photoelectric effect will not occur. Okay? So the threshold value is the value for this quantity to be 0. Sorry. Okay? So with this, I want to discover the wavelength, sorry, the work function. So this will be W equals to hc over lambda. Okay? Well, you have the value of the wavelength. It is given here in meters. And you also have the value of h, which is just a universal constant, and you also have the value of c. Can we use E equals hc over lambda equals to h bar omega? Yes, you can use h bar and omega. There is no problem with that. Okay. So you just replace here the values of h, c, and lambda. And since you want the answer in electron volt, you replace the value of h in electron volt. And the result of that is around 4.2 of around 4.3. It's more or less like this. 4.3 eeV. Okay? Is that clear? Okay. So item B says, what is the maximal kinetic energy of the emitted electrons by the incidence of ultraviolet light with wavelength of 1,500 angstrom? Well, we can first of all ask if this wavelength is compatible with the occurrence of the photoelectric effect. Well, the threshold wavelength is this one. So if I choose a wavelength that is smaller than this, then I will see the photoelectric effect occurring. So this is compatible. And now the maximum kinetic energy is this. The maximum kinetic energy is precisely this quantity here. Okay? This is the quantity I want to compute. But then you can say, well, I just have to find out the velocity and so on. But you don't have to do so, right? Because the maximum kinetic energy, let me call it K max. This is h c over lambda minus the work function. And we know the work function. We just computed that. Remember, the work function is a fixed number for each material. And the question, the problem is giving to me lambda. So I just have to replace lambda here, substitute h for its value in electron volt, the speed of light that we know, 3 times to the 8 meters per second, and subtract from this value that we just computed. Okay? Do you agree? Okay. So if you replace these letters here by those numbers, you find that this is approximately 4.2 eV. So it's very close to the value of the work function. Okay? Okay, so I hope that these exercises are clear to you now. And it's very important that if you made a mistake or if you didn't know how to do that, that after this explanation, you try to do it yourself, okay? Because here, I mean, this is the very basic application of the photoelectric effect equation. So you have to master that. You have to know how to do it, okay? Okay, so with that, I will close this session. And we'll see each other again tomorrow with the discussion about the atomic model by Niels Bohr. Okay? So have a nice day and take care. And there is a question. I will stop the recording and I'll answer your question. Okay? Okay, so bye.